This slide outlines the workflow and technical framework for pet tracking app, which integrates IoT device, cloud infrastructure, and a user-friendly mobile interface to provide real-time insights and predictable analysis for pet tracking. It highlights the detailed configuration, the efficient and real-time data transfer capability of our system, highlighting the use of IoT device and wireless communication technologies. On the left side, the image showcases how our IoT device like ESP32, Raspberry Pi, and Android phone send Wi-Fi signal strength and transmit it to nearby Raspberry Pi. These signals are processed and passed on to the connected IoT things for further communication. The right side presents a real-time log for data being transmitted and received by our IoT things. It demonstrates the continuous and reliable exchange of our information using MQTT protocols, ensuring that data is seamlessly integrated into our AWS cloud servers processing and storage, which we can see this is our real-time data transform, which sent by the Raspberry Pi on our IoT thing Android phones. As we can see, it sends the data per second, and we can receive the real-time data transform. Okay, now let's continue. And now, this slide highlights the detailed configuration and implementation of our IoT systems. On the left, we show the physical setup and network architecture of our IoT device. The devices are configured to connect, scan, and transmit signal data to cloud via AWS IoT Core. This ensures real-time monitoring and seamless data collection. On the right, the code demonstrates the real-time data transmission process, where Wi-Fi signal strength data is collected and published to an MQTT topic at 1 second intervals. Below it, you can see the AWS IoT Core successfully receiving and displaying the transmit data in real time, which we can see by this video. This is which you can see when we subscribe the IoT MQTT test client, we can receive the real-time MQTT signal strength data. And this slide illustrates the data processing pipeline, starting from IoT device transmitting signal data through IoT Core, with data stored in DynamoDB and analyzed using machine learning for advanced insights. Our data also go to AWS EC2, which hosts custom algorithms and backend service, ensuring efficient computation and seamless integration with the application. And this is our data received and stored in DynamoDB. As you can see, we receive a lot of items, more than 1,000. This is all the data we can use for machine learning and check our pack activities. And now this slide showcases our front-end user interface, which provides an interactive floor plan to display real-time pet tracking, pet locations, and facilitate intuitive tracking and analysis. Data clustering methods like the Albert method are applied to optimize the analysis, enabling predictions about pet behavior and movement patterns for future improvements. Our workflow provides a seamless integration of IoT, cloud servers, and user interface, ensuring real-time data tracking and monitor for pets.
Welcome to my part of the project update. I'm just here to talk about what we've done so far and what I think we're still gonna work on. I'm still gonna work on. So the website's working. Feature 1, real-time update. Feature 2, insights. But however, I'm just here to talk about the algorithms. The first algorithm is temporal synchronization. With that, we can solve basically the situation where ABC, they're not physically impossible to start at the same time. So basically, the timestamp synchronization is a big issue when doing triangulation. basic logic is A might be 0, 0, 0, 0, 0, 1, and 2, but B might be 0 and 1, and they might arrive at the same time, you know, without even having C into the server. So that is a huge issue. But here I'm just gonna talk about how I'm solving it. Essentially, what I'm doing is here is the triangulation algorithm. Well, we're not gonna discuss too much about it, but as you can see here, I kind of also solved the problem of, when there's difference in RSSI spikes, there are a certain possibility that the RSSIs are, let's say, abnormal, and it results in the final X percentage and Y percentage being calculated really abnormally. So if one of them is zero, like negative, I just make it positive. That's a kind of greedy method, hacky method, but I think it works. It works. And for this, it's basically saying that if there's some sort of issue where the final X percentage and Y percentage are calculated, but they're outside the confine of 100%, and that happened before as well, my solution is pretty easy. If it's bigger than 100%, I just basically do what I think is logical, is to have the fault power here. Basically, this is a what's it called, global variable, and this is the value percentage. The basically the x or y that's passed into the function, and then we use modulation operation. We get basically what is bigger than the default power, negative default power, which I set it here being 40, and then basically this is just saying that, like, what's more than, like, let's say x is 120, right? Or 122. 120 results in this whole thing being 0, and I just use 10 instead. And 122 being this result in 2, and I just basically 10 plus 2, right? And if value is still bigger than 100, I'm just gonna do this plus 10 negative threshold. Basically, there's a threshold that I could do, and else value is this, and this is basically just saying that I use recursion to actually get the correct adjustments, and that's pretty much it. The other method I used is basically saying that I have a current timestamp, whether the time how do you call it, whether it's 000, 001, or 002. Like, let's say it arrives in server A, B, C. It's gonna be 001 for A, 0000 for B, and 00002 for C, right? Since A is the first that's gotten to the EC2's flask, I'm just gonna take this timestamp as the timestamp, and I don't care about what timestamp it actually is. I only care about what the first one is, and I use that as the current timestamp. That's basically the problem, right? And for B and for C, I just wait for there is a first B, or if there is a first C, I use that, and I use these three, to make it triangulate. And if there's a situation where I've accumulated A and B but without C, I'm just gonna wait for C until there is the next first C that arrives to the server. I perform triangulation. And all of this is basically saying I have a basically temporary ARSSI, BRSSI, and CRSSI. So this is initialized before even the everything started. Well, if it's current timestamp, I change it to signal level. If not, I just make it whatever that's default. So that way, is more accurate than whatever let's say the messed up synchronization is going to result in. And the result is considered pretty good. I have it. Yeah, I have it here. Oh shit, it's not here. Never mind. So basically, not this. Yeah, so basically that's it. And for my next part, I'm thinking of implementing a algorithms where I constantly get the RSSI between A and B and B and C, and then I use that to calculate the distance and to compare to the initial distance that the user input in. So basically, the first time we set this whole thing up, we gotta ask for the user where A and B and C is. But from that time being, from that on, we already know where A and B and C is. That's the only time we require user input. And between A and B, we can calculate the distance. And since user tells us the actual distance between A and B, B and C, because we calculated using like user's input, we compare the user's input distance between our calculation, and we can adjust the parameters of tx power and the n exponential. With this method, first we can ensure the accuracy of basically where each point is and the accuracy of RSSI. Problem is RSSI might vary by environmental changes. Basically, my thought would be to implement a efficient check that happens, once. How do I say this? That happens basically from time to time. That checks, the user inputted, like the first time user inputted A and B and C's distance and our RSSI's, our calculations distance, and using that we can adjust the tx power and n, the time, and then using that we can ensure the accuracy even if the environmental changes takes place.